Hello all, my name is Avinash. I will be presenting our work on SIUNet Sparsity Invariant Unit for edge-aware depth completion. This work was funded by Fraunhofer Gesellschaft, Germany. Depth completion is the task of generating dense depth images from sparse depth measurements captured by LiDARs or laser scanners. Depth completion is challenging because of sparsity and irregular spacing between the scanned points in the measurements. Existing guided solutions require sophisticated neural network architecture and also take care of occlusion, motion artifacts, and noisy measurements coming from multiple sensors. Existing unguided methods, however, produce depth images with depth bleeding effect because they do not make use of semantic information. We use the advantages of both unguided and guided approaches. In that, we make use of semantic segmentation image available in the synthetic outdoor dataset to generate depth contour images as shown here in step 1. The idea is to learn structural information in lieu of semantic information to produce sharp edges. Hence, both dense depth image and depth contour image are used as targets during auxiliary learning step as shown here in step 2. Finally, our network is trained on real-world dataset using transfer learning by using only depth images as targets as shown in step 3. Our network consists of a stack of sparse convolution layers in the shape of a UNet. The speciality of our network is that it does not contain branchouts, since both the primary task and the auxiliary task are in the same depth domain. This means that our network has a simple architecture with end-to-end feature sharing. For training in the auxiliary setup, we combine two loss functions, namely sparse mean absolute error and weighted mean absolute error. Sparse mean absolute error is also used as an evaluation metric. Here, I present the results of our approach evaluated on KITTI depth completion benchmark. It shows that our network produces state-of-the-art result with respect to MAE and IMAE matrices. On the right side, the close-up views of our method shows the sharpness along object boundaries and the structural correctness. Depth bleeding can be observed in the reconstructions of other methods. The results for varying levels of sparsity induced in the sparse input image show that our model performs well while maintaining sharp edges in the reconstructed images compared to a standard UNet without sparse convolutional layers. Here, I present the results of our approach on an indoor dataset as the target domain. Since the network explicitly learns structural information instead of semantic information from a synthetic outdoor dataset, we can see that our network generalizes well on the indoor NYU v2 dataset as well. I conclude by presenting the summary of our work. SIUNet architecture was proposed for depth completion that relies only on LiDAR data of target domain during both training as well as inference. There are no branchouts in our network, resulting in a simple architecture with end-to-end feature sharing. Depth contour targets obtained from synthetic data for auxiliary learning allows the network to explicitly learn structural information. Using sparse convolutional layers in UNet architecture, our network is invariant even to extremely sparse inputs. Learning structural information in lieu of semantic information allows our network to generalize well on different datasets. Finally, I would like to thank the WACV chairs for accepting our work and also the organizers for providing us the platform to present our work. Thank you all for your attention.